every layer of the sun. Space is complicated. We make it simple. The sun looks like a single object. It isn't. It's at least 6 distinct layers stacked inside and around each other, each one operating under wildly different physics, at wildly different temperatures, moving at wildly different speeds. Some of these layers you could never survive approaching within 1 million kilometers. One of them, bizarrely, is colder than the layer directly beneath it. We're going in order from the furious core outward to the edge of where the sun's influence finally gives out. And by the end, the sun will stop meaning one simple ball of fire. The core. We begin at the center, where everything the sun does actually starts. The core is where nuclear fusion happens. Hydrogen nuclei slamming together with enough force to fuse into helium, releasing the energy that eventually becomes every bit of sunlight that has ever touched your skin. The temperature here is about 15 million degrees Celsius, and the pressure is roughly 250 billion times what you feel standing on Earth's surface, crushing hydrogen atoms so violently that, on average, a given proton only fuses with another proton once every few billion years, despite billions of collisions happening every single second. Fusion is almost absurdly inefficient, one photon producing event lost in an ocean of near misses, and yet there is so much hydrogen packed into such a small, furious space that the cumulative output is enough to light an entire solar system. Here's the fact that should genuinely bother you. Light produced in the core does not simply shoot outward. A single photon created by fusion can take anywhere from 10,000 to 170,000 years to escape the sun, bouncing between densely packed particles in a process called a random walk, absorbed and re-emitted over and over, traveling a few millimeters at a time before being knocked in a completely new direction. The sunlight warming your face this morning began its journey as a fusion event that may have happened before modern humans existed as a species. It has been trapped inside the sun for longer than civilization has existed, only to finally escape at the exact moment you happen to be standing outside. The radiative zone. Here's the twist. The light escaping the core doesn't immediately fly free. It enters a zone that exists purely to slow it down. The radiative zone extends from just outside the core to about 70% of the way to the sun's surface, and it's so dense that energy can only move through it by radiation, photons being absorbed and re-emitted by particle after particle. The same maddening random walk that traps light for tens of thousands of years. There is essentially no bulk motion here, no churning, no rising and falling material, just a vast, static, superheated region where energy crawls outward one absorbed photon at a time. Temperatures here range from about 7 million degrees Celsius near the core to around 2 million degrees near its outer edge, and the density drops by a factor of about 20 as you move through it, thinning out enough that the physics of energy transport eventually has to change entirely. Here's the fact that changes everything about this layer. It's essentially a bottleneck by design. If the radiative zone weren't there, if photons could somehow escape the core directly, the sun's output would be catastrophically different from what it is now. The radiative zone is the reason sunlight arrives on Earth as a slow, steady trickle of energy accumulated over millennia, rather than an uncontrolled burst. The boundary where the radiative zone ends is called the tachocline, a thin transitional layer where the sun's rotation itself changes behavior. Inside it, the sun rotates almost like a solid body, and outside it, different latitudes rotate at different speeds. Some solar physicists suspect the sun's entire magnetic field, the one responsible for sunspots, flares, and solar storms, is generated right here, in the friction of two regions of the sun trying to spin at different rates. The convective zone. Here's the reframe. Once energy makes it past that bottleneck, it stops moving quietly. The outer 30% of the sun's interior is cool enough and thin enough that radiation alone can't move heat efficiently anymore, so the sun switches strategies entirely and starts physically churning. Hot plasma rises in massive columns from the base of this layer, cools as it nears the surface, and sinks back down to be reheated, an enormous continuous boiling motion called convection, the exact same basic process that moves a pot of water on a stove, just on a scale of hundreds of thousands of kilometers. This churning is what produces the mottled, grainy texture visible on the sun's surface through a solar telescope, a pattern called granulation, where each individual granule is a single convective cell, roughly the size of Texas, rising and falling in a cycle that lasts only about 10 minutes before that specific cell breaks apart and reforms elsewhere. Here's the fact that should genuinely unsettle you. This constant churning, combined with the sun's rotation, is what generates the sun's entire magnetic field through a process called the solar dynamo, the same violent, chaotic motion responsible for every sunspot, every solar flare, and every coronal mass ejection that has ever disrupted satellites or power grids on Earth. The convective zone isn't just moving heat, it's the engine room generating the invisible force field that reaches all the way out past every planet in the solar system, the photosphere. Here's the pivot. This is the layer you're actually looking at when you look at the sun, and it's simultaneously the thinnest and, in some ways, the most misleading. The photosphere is only about 500 kilometers thick, a sliver compared to the sun's radius of nearly 700,000 kilometers. And yet it's the layer that defines what we call the sun's surface, because it's the first point where the plasma becomes thin enough for light to finally escape freely into space instead of being reabsorbed. Its temperature is around 5,500 degrees Celsius, dramatically cooler than the layers both directly beneath and, strangely, directly above it. This is also where sunspots appear, darker, cooler patches, still blisteringly hot at around 3,800 degrees, but cool enough relative to their surroundings to look dark by comparison. Sunspots form where intensely concentrated magnetic field lines from the convective zone punch through the surface, suppressing the churning motion beneath them and locally blocking some of the rising heat. Here's the fact that changes everything about how you should picture this layer. It isn't solid, isn't a shell, and doesn't have a hard edge at all. The photosphere is simply the depth at which the sun's gas transitions from opaque to transparent, a boundary of visibility, rather than a boundary of material. If you could somehow fly a spacecraft toward the sun, there would be no moment of crossing a surface. There would only be a gradual, continuous thickening of the same superheated gas, all the way down. Before we leave the visible surface behind, it's worth sitting with just how violent the photosphere's calm appearance actually is. Despite looking from Earth like a smooth, static disk, the photosphere is in constant, roaring motion. Sound waves generated by the churning convective zone directly beneath it ripple across the surface continuously, at frequencies far too low for human ears but easily measured by instruments, causing the entire surface of the sun to oscillate, rise, and fall by tens of kilometers every few minutes. This field of study, called helioseismology, works almost exactly like using earthquakes to map the interior of our own planet. By tracking how these sound waves ripple, bend, and echo across the visible surface, physicists have been able to reconstruct the structure, temperature, and even the rotation rate of layers hundreds of thousands of kilometers beneath the surface, all without ever being able to see directly through the sun's opaque outer layers. Here's the fact that should genuinely bother you. Helioseismology has revealed that the sun's interior doesn't rotate as a single, rigid unit the way a solid ball would. The core and radiative zone rotate together roughly once every 27 days, but the convective zone above them rotates differently depending on latitude, with the equator completing a rotation faster than the poles, a phenomenon called differential rotation, and one of the primary sources of the twisting, tangled magnetic stress that eventually erupts as sunspots, flares, and coronal mass ejections. The surface you can casually glance at with a solar filter is, underneath its stillness, ringing like an enormous, continuously struck bell, the chromosphere. Here's the twist that breaks basic intuition. Moving outward, away from the sun's furious interior, temperature should keep dropping. Instead, it starts climbing again. The chromosphere sits just above the photosphere, only a few thousand kilometers thick, and its temperature rises from around 5,500 degrees at its base to as much as 20,000 degrees near its outer edge, hotter than the visible surface directly beneath it, for reasons that are still not fully settled science. Under normal daylight, the chromosphere is invisible, completely washed out by the overwhelming brightness of the photosphere below. It's only visible during a total solar eclipse for the few seconds right before or after totality, when it flashes into view as a thin, reddish pink ring around the sun's blacked out disk, colored by the specific wavelength of light emitted by hot hydrogen. This is also the layer responsible for solar prominence's enormous glowing arcs of plasma that erupt outward along magnetic field lines, sometimes stretching hundreds of thousands of kilometers into space, large enough to dwarf the entire planet Earth many times over, briefly visible as looping, fiery structures before collapsing back down or breaking free entirely. The corona. Here's the fact that should genuinely bother you more than anything else on this list. The outermost layer of the sun's atmosphere is, by a staggering margin, the hottest place in the entire system, millions of degrees Celsius, hundreds of times hotter than the visible surface directly beneath it, despite being much farther from the fusion happening at the core. This is one of the most stubborn open problems in solar physics, known as the coronal heating problem. Nobody has fully explained why the corona is so dramatically hotter than the layers closer to the source of the sun's energy. Leading theories point to magnetic reconnection, tangled magnetic field lines from deeper layers snapping and reconnecting near the surface, releasing bursts of energy directly into the thin plasma above, but a complete confirmed explanation still doesn't exist. The corona is also where the solar wind originates, a constant outward stream of charged particles blasting away from the sun at speeds up to 800 kilometers per second, flowing past every planet in the solar system and eventually carving out a vast bubble called the Heliosphere, which extends far beyond the orbit of Pluto before finally giving way to interstellar space. Here's the fact that should worry you a little more than the rest. When the corona's magnetic field lines snap and reconnect violently enough, they don't just heat the surrounding plasma, they can hurl an enormous bubble of magnetized material, a coronal mass ejection, directly outward into space at speeds of several million kilometers per hour. If one happens to be aimed squarely at Earth, it can slam into our planet's magnetic field a day or two later, triggering a geomagnetic storm capable of inducing rogue electrical currents in long distance power lines and pipelines. In 1859, an event now called the Carrington event did exactly this, at a scale unmatched in the modern instrumental record. Telegraph systems across Europe and North America failed. Some operators reported their equipment sparking and catching fire, and aurorae, normally confined to polar latitudes, were reported as far south as the Caribbean. A coronal mass ejection of that same magnitude, striking a modern, electrically dependent civilization, is estimated by some risk assessments to be capable of causing trillions of dollars in damage and knocking out power across entire continents for months, simply because our infrastructure in 1859 had almost nothing to disrupt, and today's does. Here's the part that lingers. The corona has no hard outer edge at all. It simply thins out gradually over billions of kilometers until the density of solar particles becomes indistinguishable from the particles drifting between stars. In a very real sense, the sun doesn't end at a boundary. It fades, the heliosphere. Here's the final layer, the one that isn't really part of the sun at all anymore, but is entirely made from it. Beyond the corona, the outward flowing solar wind keeps pushing, carrying the sun's magnetic field with it, inflating a colossal bubble of charged particles that swallows every planet, every asteroid, and every comet in the solar system. This bubble, the heliosphere, extends roughly 18 to 20 billion kilometers from the sun at its nearest edge, well over 100 times farther than Earth's own orbit, before the pressure of the solar wind finally weakens enough to be overwhelmed by the pressure of the interstellar medium, the thin gas and dust drifting between star systems. That boundary is called the heliopause, and it isn't a hard wall so much as a turbulent, shifting frontier where the sun's influence and the galaxy's influence push against each other in a standoff that never fully resolves. Only two human made objects have ever crossed it: Voyager 1 in 2012 and Voyager 2 in 2018, both confirming the crossing by detecting a sudden, measurable jump in the density of surrounding plasma as they left the sun's bubble and entered true interstellar space for the first time. Here's the fact that should genuinely bother you. Even after crossing the heliopause, the Voyager probes were not free of the sun. They remain gravitationally bound to it, still technically orbiting, just on a path so wide it will take tens of thousands of years to complete a single loop. The sun's light and heat may functionally end at the heliopause. Its gravity does not end at all, it just gets weaker forever without ever quite reaching zero. The solar cycle. Here's the part that ties every layer back together. The sun doesn't behave the same way year to year. It runs on an approximately 11-year rhythm called the solar cycle, swinging between a quiet phase called solar minimum and an intensely active phase called solar maximum, driven by the churning, twisting magnetic dynamo generated deep in the convective zone. At solar minimum, the sun's surface can go almost entirely blank, sometimes with zero visible sunspots for weeks at a stretch. At solar maximum, the surface becomes riddled with sunspots, and the sun dramatically increases its output of flares and coronal mass ejections. Massive eruptions of magnetized plasma hurled outward into the solar system, some powerful enough, when aimed directly at Earth, to distort our planet's own magnetic field, disrupt satellites and power grids, and paint the sky with auroras far outside their normal polar range. Here's the fact that lingers. Astronomers still don't have a complete first principles explanation for exactly why the cycle takes 11 years specifically, rather than 5 or 20 or some other number entirely. It emerges from the complex, chaotic interaction between the sun's rotation and its churning interior, and reproducing that exact rhythm from theory alone remains an unsolved problem. Every layer described so far, the churning convective zone, the magnetic tangle of the corona, the sunspots dotting the photosphere, is in a sense just one long running argument between the sun's rotation and its own magnetic field, replaying itself on an 11-year loop that has been running since before there was anyone around to notice. Let's sort these 8 again, a different way, not by distance from the center, but by temperature. On the hottest end, the core at 15 million degrees and the corona at several million degrees, the two extreme opposite ends of the sun somehow tied for the top of the list, despite one being at the very center and one being at the very edge. On the coolest end, the photosphere, the visible surface, dramatically colder than almost every layer around it in both directions. On the most violent end, the convective zone physically churning hundreds of thousands of kilometers of plasma every 10 minutes. On the most patient end, the radiative zone, where a single photon can take over 100,000 years just to cross it. And on the most unexplained end, the corona, hot enough to defy easy explanation, home to one of the most stubborn unsolved questions in the study of our own star. Every layer of the sun runs on a slightly different rulebook, and somehow, together, they produce the single steady disk of light that every living thing on Earth has built its entire existence around. Here's the last thing worth sitting with. You have never actually seen the sun's core, and you never will. Its light takes tens of thousands of years just to escape the layer directly around it, meaning the fusion happening right now, at this exact moment in the center of the sun, won't be visible from Earth until long after everyone reading this sentence is gone. Every photon warming your skin today started that journey during an era of Earth's history you couldn't name without looking it up. The sun feels immediate. It is, in the most literal sense, an extremely old message, only just now arriving. Not bad for stick figures on a rock.